Now we turn to the C memory model. Up to here, we talked about cost. Next, we look at where our data actually lives in memory and why C makes us think about it. This course leans on 5 facts about C. Think of this as a quick refresher. Let's walk through the 5. First, a pointer. A pointer is a variable whose value is an address. $P reads what it points at. Second, a struct. Its fields sit in order at fixed offsets, though the compiler may add padding for alignment. So s.f or p_f is just the base plus a fixed offset. Third, an array. Its elements sit right next to each other in memory. The address of A at index I is the base plus I times the size of one element. Fourth, stack versus heap. Locals live on the stack and clean up by themselves. Memory from malloc lives on the heap, and you must free it yourself. Fifth, malloc and free. Malloc asks for a heap block. Free returns it. Free each successful allocation exactly once through the handle that owns it. One rule to remember. Real production code checks every malloc for null. Our slides sometimes drop that check to keep the teaching line short. Never read that as permission to skip it. A running C program uses 3 regions we care about. Let's look at each one. The stack holds your locals and your function parameters. Each function call pushes a new frame. When the function returns, its frame pops off on its own. The heap is memory you ask for with malloc and give back with free. It is flexible, but the cleanup is manual. It is your job. The static or global region holds your global variables and your static locals. It has one fixed place for the whole run. Next slide. The shape almost every data structure follows. Most data structures in C follow one shape. A small handle sits on the stack and owns a big block on the heap. The pointer on the stack points into the heap. Lose the handle and you leak the block. This picture sums it up. The stack cleans itself like trays that pop off a pile. The heap is manual. Malloc hands you a block, and free is how you give it back. Let's read the one program in this course that prints real addresses. First, a static variable gcounter. Static storage gives it one fixed address for the whole run. Next, a local variable is set to 10. A local like this lives on the stack. Then R, an array of 4 ints. These 4 ints sit right next to each other on the stack. Now a heap block. Malloc gives us room for 4 ints on the heap, and heap points to it. We check the result. If heap is null, malloc failed, so we return. Always check every malloc. This loop fills the heap block. Each slot gets 100 plus I next slide. We print the address of every one of these. Now we print the addresses. This line prints the address of the static gcounter. This line prints the address of the stack local A. This line prints the address of R at index 0, the first element. This line prints the address of R at index 1. Watch this one. It should land exactly 4 bytes past the first element. The last line prints the address of heap at index 0, the first slot on the heap. Before the next slide, predict this. Will the stack local and the heap block land near each other or worlds apart? A pointer variable has its own location, and it also stores an address. These are 2 different things, and they are easy to mix up, so let's separate them carefully. Think of the sticky note again. The note itself sits somewhere, say in your left pocket. That spot is the pointer's own address. In C, we write it as address of P. What is written on the note is a different thing. The note says 214. That is the address the pointer holds. In C, that is just P. And when you follow the note to room 214 and look inside, that is dereferencing, written star P, so keep them apart. Where the note lives, address of P, is not the same as what the note says. P mixing those two is the most common pointer mistake. This is one real run of the program. It printed 5 addresses, one for each variable. Look at the 2 stack lines. The address of R at index 1 is exactly 4 bytes past the address of R at index 0. That is because ints are 4 bytes, and array elements sit right next to each other. Now compare the regions. The stack addresses start with 1, 6b. The heap address starts with 1, 0, 4. They are far apart. The stack and the heap live in very different parts of memory. One warning: these exact numbers will differ on your machine, and even between 2 runs, because of address randomization and the allocator. So read the relationships, not the digits. That is why no other program in this course prints raw addresses. From here on, our diagrams use round, made-up decimal addresses, like 5,000, 7,000, and 6,000. They are chosen to be easy to read and put out of order on purpose. This is a convention for all 21 decks. These diagram addresses are only for teaching. Heap blocks start around 5,000 and step by the type size. An int is 4 bytes. The stack sits far away, around 2,000. They are out of order by design, and malloc will never hand these exact numbers back. Real addresses vary on your machine. They exist to show that a field stores an address, and which address changes. So in a diagram, when you see 5,000, read it as some heap address, illustrative, not real. When you see next equals 7,000, it means this field stores the address of another node. And when you see null, it means it points at nothing, the end of a list or an empty slot. Let us read one memory map together. This is the picture you will see again and again in this course. On top is the stack, below it is the heap. Both live in one big address space. This row is our pointer, called P. It lives on the stack. A pointer is a small box that holds one address. Here P holds the start address of a block down in the heap. The pink color links P to that block. This row is the start of the heap block. It is the first integer at index 0, and it holds the value 10. The whole block is 5 integers in a row, 20 bytes in all. Next slide. What owning this block really means. So the shape is simple. A small handle on the stack owns a big block on the heap. If you lose P before you free the block is still there, but nothing points to it. You can never reach it again. We call that a leak. Now let us watch the life of one heap block step by step. Step 1. We write a pointer named P on the stack. Right now P has no meaningful value. We say its value is indeterminate. Do not read it yet. Step 2. We call malloc. If malloc succeeds, it gives us a fresh block down in the heap. This green block is that new memory. And now P holds the start address of that block. The pink link shows it. P sits on the stack and points into the heap. The block belongs to P. Step 3. We call free on P. Free makes the block available to reuse. But look at P, it still holds the old address. That address now points into freed memory. We say P dangles. Reading through it is a bug. Step 4. Right after the free, we set P to null. Now P points at nothing. Reading through null is still undefined behavior, but it usually crashes right away instead of silently corrupting memory. And note that setting this P to null does not fix other copies of the old address. So the rule is short. Free every block exactly once through the handle that owns it, and right after you free P, set P to null. Then you could never read a dead address by accident. Our lessons use two languages. One is pseudocode, the clean plan. Here the pseudocode tests if x equals nil. Nil is the word for nothing. It means this link goes nowhere. On the right is the very same idea, but in CC writes it as null. So if x equals null, there is no node here and we stop. Carry this bridge with you for the whole course. Pseudocode nil is exactly C null. When a next field or a left or right field holds nil or null, it is a link to nothing. It marks the end of a list, a missing child, or an empty slot. Why is reading A at index I so fast? Because the computer does not walk the array. It does one small sum. This box shows that sum. The address of A at index I equals the base address plus I times 4. We use 4 because here an int is 4 bytes wide. Look at the strip below. Index 0 holds the value 10, and it sits right at the base address. This is where the array begins. Index 1 holds 20. Its address is the base plus 4 bytes. That is one step of 4. Index 2 holds 30. Its address is the base plus 2 times 4, which is 8 bytes past the start. One multiply and we are there. And this is the array's superpower. Index 2 or index 2 million cost the very same. One multiply, one read. That is why we say reading A at index I is big, O of 1 constant time. Next slide, try one address yourself. Try one yourself. An int array starts at base address 2000. What is the address of A at index 5? And what changes if it is an array of doubles, where each one is 8 bytes wide? For int, the address is 2000 plus 5 times 4, which is 2020. For doubles, it is 2000 plus 5 times 8, which is 2040, because now each step is 8 bytes. The size of one element sets the stride.